Let us learn about the fourth property of orthogonal matrices. If A is an orthogonal matrix, then A is non-singular. So it is given to us that A is an orthogonal matrix. So we have to show that matrix A is non-singular and A inverse is equal to A transpose. Okay. If A is orthogonal, then it will be non-singular matrix and its inverse will be equal to its transpose. This is what we have to prove. Now, from property number 1, what do we know? From property number 1, which we have already learned in the previous lectures, this was the property number 1, that if A is an orthogonal matrix, then determinant of A is equal to plus minus 1. This is the fact which we have already learned in this lecture series previously. If you haven't watched the previous lectures, then go to the link in the description, and in the description you will find the playlist. Just click on that playlist and watch from the very beginning. So matrices playlist, if you watch from the very beginning, you will understand each and everything. Okay. So all the lecture series which I am making, these are meant to be watched from the beginning. These lecture series are meant to be watched from the beginning itself. Only then you will understand. We are learning everything in series. Okay. So if A is an orthogonal matrix, then determinant of A is equal to plus minus 1. This we have already learned, and we have learned the proof also. Okay. This was the proof which I had already discussed in the previous lectures. This much long was the proof. Okay. So if the matrix is orthogonal, then its determinant is plus minus 1. Its determinant is plus minus 1. So if A is an orthogonal matrix, then determinant of A is equal to plus minus 1. Now, if determinant is equal to plus minus 1, it implies that A is non-singular. How? Because determinant equal to determinant of A is equal to plus minus 1 implies what? It implies determinant of A is not equal to 0. Okay. And if determinant of A is not equal to 0, it is non-singular. Okay, because determinant is equal to plus minus 1. So as determinant is equal to plus minus 1, so it is not equal to 0. So it is not equal to 0, and if it is not equal to 0, then A is non-singular, because for determinant equal to 0 we have singular matrix. Okay, if determinant of a matrix A is equal to 0, then A is singular matrix. Okay, then A is singular matrix. This fact you already know. Okay, but over here the matrix determinant is equal to plus minus 1. So determinant is equal to plus minus 1 means that determinant is not equal to 0. If determinant is not equal to 0, then A is non-singular. Then matrix A is non-singular matrix. Now if a matrix is non-singular, its inverse exists. Okay, an important property of a non-singular matrix is that its inverse exists. So A inverse exists because A is non-singular, its determinant is not equal to 0. So A inverse will exist. So A inverse matrix will exist. Now from the definition of orthogonal matrices, what do we have? From the definition of orthogonal matrices, A transpose is equal to identity matrix, and it is equal to A transpose A. It is equal to A transpose A. How? This is from the definition. This particular statement is from the definition of orthogonal matrices. From definition of orthogonal matrices. Now consider this much only, the first half only. Okay, let us consider only the first half. What is the first half? This much only. Let us consider this much only, which is the first half. Ignore this part. Okay, this part ignore. Just consider the first half. So A transpose, what is it? It is A transpose is equal to I. Okay, A transpose is equal to I is what we have to consider. A transpose is equal to I is what we have to consider. So A transpose is equal to I, which was the first half. Now multiply both sides by A inverse. Okay, so A transpose is equal to I. If you multiply both sides by A inverse, what will happen? So we have initially A transpose is equal to what? It is equal to I. Multiply by A transpose on both the side. A inverse on both the side. If you multiply by A inverse on both the side, something like this will happen. Okay, something like this will happen if you multiply by A inverse on both the side. Multiply by A inverse on this side also, and multiply by A inverse on this side also. So let us see the expression matches or not. Okay, let us see. So the expression matches. A inverse A transpose is equal to A inverse I. Now if you multiply with identity matrix, the matrix remains unchanged. So A inverse multiplied by I will be equal to A inverse itself. From this property, A multiplied by identity matrix, matrix A multiplied by identity matrix is equal to matrix A itself. Okay, so A inverse matrix multiplied by identity matrix will be equal to A inverse matrix itself. Okay, and just group these two terms together. These are three terms, so group the first two terms together. So we have grouped the first two terms together, and A transpose has remained as it is, and these two initial terms have been grouped together. Okay, now we already know from the property that A inverse A is equal to identity matrix from the definition of inverse. From the definition of inverse, A inverse A is equal to identity matrix. Matrix A inverse multiplied by matrix A is equal to identity matrix. So A inverse multiplied by A is equal to identity matrix. A transpose has remained as it is. A inverse has remained as it is. So now identity matrix multiplied by any matrix is equal to the same matrix. So A transpose will remain A transpose no matter whether you multiply with I or not. So A transpose remained A transpose. A inverse remained A inverse. So A transpose came out to be equal to A inverse. Okay, and we can also say A inverse is equal to A transpose. So we have successfully shown what? We have successfully shown that A inverse is equal to A transpose. This is what we had to show in the beginning, that A inverse comes out to be equal to A transpose. So in the beginning we had to prove this only. Prove that A inverse is equal to A transpose. A inverse is equal to A transpose. So following the steps we have proved. Following the steps we have proved that A inverse is equal to A transpose, or A transpose is equal to A inverse. Both the way you can say it both the way. A transpose is equal to A inverse, or A inverse is equal to A transpose. Okay. If A is orthogonal, these two conditions, that A transpose is equal to A inverse and A inverse is equal to A transpose, both this condition will hold when A is orthogonal. When A is orthogonal, only then these two conditions will hold. Okay. If A is orthogonal, only then these two conditions will hold. It is all given to us in the beginning itself that A is orthogonal. Okay. If A is orthogonal, only then these conditions will hold. It is not a general condition. Okay. Remember this thing. It is not a general condition.